Ladies and gentlemen, welcome to my shop. Recently I finished the restoration of this old tool grinding machine. I did a few test cuts with different setups, hoping to be able to use this machine for small surface grinding jobs occasionally. But unfortunately the results were quite disappointing. So let's have a closer look at the somewhat dubious spindle design. First problem, the bearings are here and there, and the distance between the grinding wheel and the bearings is quite large. This might be a problem, especially in conjunction with the small diameter of the spindle. Well, this might still work. But I think the main issue are the actual bearings. The machine has self-aligning spherical roller bearings. You can hopefully see that the inner race is free to tilt against the outer race. This is one of the original bearings which is completely destroyed, so I replaced them, but I think that this type of bearings is not ideal for the application. Another problem is that the bearings are mounted onto the shaft by means of conical adapter sleeves. The inner race of the bearings is tapered and matches the cone of the sleeves. This goes onto the spindle and the sleeve is pulled into the cone by a lock nut. You can see the lock nut here. This design makes it almost impossible to position the bearings at defined locations, and I don't see any way to put a defined preload on the bearings. Let me measure the play of the spindle. I will bring the camera in a bit closer so that you can see what is happening. You can see that there is a lot of play, at least 50 microns. If you look closely, you will notice that the inner bearing race is moving. There isn't any preload on the outer race right now, so I will remount the flange in order to put some preload on the outer races of the bearings. I tighten these screws lightly and as uniformly as possible. Put the indicator on again. There is still some play in it. And you can see that the spindle doesn't move back to its original position. So there's some kind of hysteresis. That's not good. Maybe plus minus 5 microns? This doesn't look right to me. And you can also hear the unhealthy sound of the spindle, even with new bearings. I double-checked with a 1 micron indicator. Plus 3 microns, minus 2 microns. I considered a redesign of the spindle based on proper spindle bearings, but an old Fortuna spindle from my "maybe I will need this one day" pile sprang to my mind. I disassembled, cleaned, lubricated and reassembled the spindle, and I came up with the following basic design. A long time ago I bought two box-shaped cast iron profiles. This was the right opportunity to make use of them. I intended to bore out a hole to receive the spindle. A massive ring should be clamped onto the original column of the machine to hold the main body. Okay, enough talk, let's make some chips. I started with the main body. This will be the location of the bore receiving the spindle. I intended to join the profiles with bolts and glue them together. I drilled the bolt holes. Improvised stops came handy. Then I realized that it was impossible to insert the hex head bolts as they were too long. So why not using curved bolts maybe? Well, I cleaned the parts and glued them together with high tensile epoxy. And, of course, threaded rods came to the rescue. All surfaces were cleaned up with shell and mill. The operation required the entire 400 mm travel of my Thiel milling machine. The next operation was boring out the 80mm hole to receive the spindle. As I wanted access to both ends of the hole, the work was mounted overhanging the table and the overarm cranked out accordingly. The table was adjusted so that the reference surface of the part was in alignment with the z-axis. The vertical head was aligned in the same manner. The center of the bore was located and drilled. As my largest twist drill has only 25mm, I try to abuse different milling cutters to enlarge the hole. Finally, this one worked pretty well. Time for some Wohlhaupter action. I used a high-speed steel cutter in the facing and boring head. The process was slow but steady. As you can see, I did not bore out the full depth in the first step. When I hit the walls, the depth of cut had to be decreased to cope with the interrupted cuts. I did not bore to the full diameter in the initial roughing phase. The process was repeated with a longer boring bar for the middle section of the work. It turned out that even the longest boring bar from my Wohlhaupter set was too short to bore the bottom part. Thus I borrowed a 20 mm boring bar from my lathe and made a sleeve to adapt it to the required 22 mm bores of the head. This worked really well despite the pretty long stick out. As before, I did not cut to the full diameter. Now, as the bore was roughed out, it was time to enlarge the diameter of the middle section to slightly more than 80 mm. I set the quill stop to the desired range and bored the section to approximately 80.5 mm. For the final precision boring, I set my digital micrometer using the actual spindle as a reference. My precision bore gauge was zeroed using the micrometer. A word of caution here, do not just set the micrometer to the desired value based on the display or vernier scale, as there might be a tiny little bit of play in the micrometer screw, similar to backlash. To keep the tool pressure as small as possible, I sharpened the insert used in the boring bar on my diamond wheel. It doesn't look pretty, that's why I need a tool grinder, but it did the job. I reached an undersize of 44 hundredths after a series of light cuts. On the Wohlhaupter I added 10 hundredths of a millimeter on the diameter. The result was an undersize of 34 hundredths of a millimeter, so that was exactly the expected measurement. In order to split the remaining difference in 3 equal parts, I added 11 hundredths of a millimeter on the boring head. Again, with an undersize of 23 hundredths, the result was exactly as expected. So I added another 11 hundredths. This cut resulted in an undersize of 14 hundredths, so that was a little bit more than expected. To be on the safe side, I just added 12 hundredths. I ended up at 100th millimeter undersize. To be on the safe side, I checked with the spindle, which almost went in, but the fit was too tight. A final spring pass resulted in a perfect sliding fit. And the final measurement told me that the bore was 100th of a millimeter oversize. Finishing the top bore was done with a tiny, very sharp horn boring bar in the same manner. Looked like a perfect fit. The play of the spindle in the housing was clearly below 100ths on both sides. I considered several methods for clamping the spindle in the housing and decided to use split clamping rings. I made 2 of them from scrap material with the ID slightly undersize and cut them on the milling machine. Holes for tensioning bolt were drilled and tapped. Holes to mount the ring onto the housing were drilled and counterbored. I drilled and tapped the threads for mounting the rings to the housing. The bore was centered with an edge finder off camera and the holes drilled and tapped using the DRO. Finally, I had to bore the rings to the final size. I did this in the final mounting position and started by rechecking the centricity of the bore holes of the main body. The ring was mounted onto the body with washers as spacers to prevent scratching the finished bore.
Bastard.
A few light cuts brought the ID to the desired 80 mm. The measurement wasn't super critical as the rings will be tangent anyways, thus using the digital calipers was sufficient. Honestly, 79.99 looks perfect, but I really wouldn't bet on this measurement. However, the test fit looked really good, a nice tight sliding fit. The same procedure was repeated on the opposite side of the part. Next was the heavy ring, which is used to mount the spindle holder on the machine's column. The desired ID was 105.08 millimeters. I bought a big lump of steel, OD 165 millimeters, length 95 millimeters. As my trepanning attempt failed miserably, I drilled and bored out the inner diameter on my torsa lathe. The faces and OD of the part were cleaned up. I intended to use clamp screws to mount the ring on the column. To drill the threaded holes, I centered the work on the forger chuck, mounted on the dividing head. The head was tilted by 90 degrees. I added a few shims underneath the work for additional support. Positions of the holes were center drilled. and drilled with a 10mm twist drill. To avoid any further damage of the column, I intended to add brass pads between the clamp screws and the column. This required counter bores from the inside of the bore. I intended to use a T-nut or woodruff cutter for this purpose. I found a pretty old one with a matching shaft diameter in my collection. The problem was that this cutter cuts just the outer 14 to 20mm range of the bore, but did not remove any material in the 10 to 14mm range. Thus, I resorted to a boring bar with a 10mm shaft, like the T-nut cutter. I abused the trailing edge of the cutter as some kind of inverted countersink. This removed enough material in the inner range of the bore so that I was able to finish with a T-nut cutter. The holes were counterbored from the outside to accommodate the bolt heads. I started tapping the threads under power and finished them manually. The inner counterbores looked really nice. A pity that no one will be able to see them when the part is installed. Finally, the holes used to mount the ring on the body were drilled and counterbored. At this point my camera decided that showing yet another drilling operation would be too boring. Thus I can just show you the counterboring and chamfering procedure. A little oops here, I realized that I had forgotten two of the counterbores. I made the brass pads by stacking and gluing the brass sheets and turning them to the desired diameter on my MCO lathe. To hold the pads in place during the installation, I glued them with the sealing compound into the inner counterbores. This stuff stays somewhat flexible and doesn't affect the clamping action. Time to mount the ring to the body of the spindle holder. The flat belt pulley was the final part required for a test run. As the spindle has conical noses on both ends, the first task was setting up the compound slide of my Emco lathe. I used the grinding wheel flange which came with the spindle as a reference. It was centered in the 4-jaw chuck. I intended to set the compound slide by sweeping the inner cone of the flange with the dial test indicator. Unfortunately, my DTIs couldn't reach far enough into the bore. Fortunately, I had an inductive millimar sensor at hand. Using this submicron precision device sounds like total overkill for the purpose, but it did the work. I turned a conical shaft as a test piece, which turned out nicely. The actual flat belt pulley was made of aluminium. Starting with the usual facing operation and drilling a hole to start the conical bore. The boring bar had to be set up upside down, so I could cut the rear side of the cone without readjusting the compound slide. The previously turned tapered shaft was used as a reference. A little moment of shock here. Fortunately, it was just a chip. The final step was turning the crown of the pulley. I intended to approximate the spherical surface by turning two 1-degree tapers from both sides and smoothing the transition with a file and emery paper. Turning the cylindrical OD was the first operation. To set the angle of the compound slide, I mounted a dial indicator on the slide and set it to the center height of the lathe. The required radial displacement equals the travel of the compound slide, 25 mm in this case, times the tangent of the included angle, 1 degree, which results in 43 hundredths of a millimeter. After a few iterations of tapping and checking, I ended up at 42 hundredths of a millimeter, certainly good enough for the purpose. The left third was turned to the 1 degree cone. The process was repeated on the right hand side. The OD was marked to help visualizing the filing and sending operation. The transitions between the cylindrical and conical sections were rounded off with a file. I finished with 220 grit sandpaper. The pulley was parted off. Turning the ID and OD with a single setup guaranteed perfect concentricity. I had to switch to a parting off blade to finish the operation. Perfect. Time for a first test run with the temporarily mounted motor. Looks good. That's it for now. Hope you enjoyed my little project. Thanks for watching and see you next time.